All right, ladies and gentlemen, 5 p.m., exactly 5 p.m. Central European time. So I guess we can kick things off. Very excited to see so many of you in today's session, and welcome to a new Synera webinar together with our partner Diabatix. And in today's session, my colleague Andrew Sartorelli, Roxanne von Mellert from Diabatix, and I will demonstrate how automated solutions address the challenges associated with battery pack design. So why are we doing this in the first place? The manual integration of various design objectives, so let's say we talk about energy densities, lifespan, safety, or maybe even cost involved, have proven to be a significant hurdle for battery pack designers. These conflicting goals require a delicate balance, but most often the current tools available at our fingertips often fall short in accommodating what we call the key performance indicators during the design phase. One of the primary obstacles faced by battery pack engineers is the lack of a cohesive environment that seamlessly integrates various tools for measuring these KPIs. Often, the connections between these tools are what we call fragile or inaccessible, which leads to a disjointed product development process. And this, in turn, forces us engineers to spend hours and hours manually updating CAD designs to reflect changes, hampering rapid innovation and iteration. And obviously, in today's very collaborative engineering landscape, it's imperative to bring together multiple disciplines to develop a successful product, and as we'll talk about in today's webinar, battery pack design. However, the challenges arise when boundary conditions change, leading to a breakdown in the repeatability of the classical, what we call computer-aided engineering, short CAE. This frustration can lead to suboptimal designs due to a lack of time for thorough iterations and ultimately delay time to market. So the question that we're trying to solve in this webinar, actually solving in this webinar, is how do we solve that problem? And that will be answered by the demos from Andrew and Roxanne in today's session. Now, ladies and gentlemen, imagine a scenario where design and analysis are harmoniously synchronized within a singular platform. This would enable engineers to rapidly adapt to shifting requirements while maintaining a holistic view of the design. By providing a connected environment that bridges the gap between design objectives and analysis outcomes, engineers can iteratively refine battery pack designs without the manual bottlenecks that currently plague the process. So, how does it look like, or how are battery packs being developed today? So fundamental principles of modern software development led to a drastic improvement to working efficiency of software developers. But, and this is a big but, none of these principles are available in engineering today. So at Synera, we recognize the need for a transformative shift of how battery pack design is approached. Much like our work in other fields, we believe that engineers should shift their focus from solely developing products to refining the underlying process. And this transition can save valuable resources and drive sustainability by allowing us engineers to iterate designs effectively, adapt to changing conditions, and ultimately achieve optimal results and performance. By connecting engineers, designers, and analysts through a unified workflow, we envision a future where battery pack development is not constrained by manual tasks or rigid processes. And we've witnessed the power of this approach in other industries where the application of streamlined workflows has resulted in exceptional efficiency gains. Applying these principles to battery pack designs, as we will see, we are confident that engineers can achieve similar success. And Synera empowers engineers to collaborate seamlessly, capture knowledge effortlessly, and replay insights across various stages of the design process, as Andrew will show in a couple of minutes. And a surprise, to show this in action, I have brought two experts today to the session. Firstly, my colleague Andrew Sartorelli, who will delve into the critical aspects of our battery pack design workflow, and he will lead you through the live demonstration. Maybe a quick hi from you and Andrew.
Thanks, Joseph. It's a pleasure to be here and be able to share a bit of what we've done with our partner at Diabatix in terms of creating workflows. And yeah, I think you guys will have a great time today.
Excellent. Thanks, Andrew. And last but not least, we have Roxanne here, who will demonstrate how you can overcome the complexity and accelerate design cycles using Coldstream. Maybe also a hi from your end, Roxanne.
Hi, hello, everyone. Thank you, Synera, for having me in this webinar. I'm quite excited to show you all what we can do with our software.
Amazing. And with that, I'm going to hand over to Andrew.
Thanks, Joseph. So we're going to dive in today to a quick demo. I'm going to keep it short on the slides because I think the most interesting thing we can do is dive into the software. And a few things that we're going to go through today. We're going to take a look at the connection to Coldstream from Diabatix. Now we can use this to actually optimize cooling plate designs for battery modules. We're going to look at how we can actually go ahead and come up with some configurations for nesting of different cells. We're going to talk about how this all integrates with simulation and also some of the core capabilities of Synera in terms of integration with parametric CAD tools. So as I said, short with slides, one slide, I'm going to go ahead and jump right into the software and give everyone a quick overview of Synera and the quick workflow we've come up with today. So hopefully everyone can see my screen now.
Perfect.
And I see we can. So what we're going to go through today is actually how we can go from coming up with a traditional design like we see on the right-hand side to something like we see on the left-hand side for battery cold plate. But first, let's just do a little bit of an introduction to Synera for folks that aren't familiar with us. So Synera is a low-code platform, a visual programming environment that really connects engineering tools from a lot of different places together. And so, what is low code? Well, really it's about creating workflows pretty seamlessly, pretty easily, just by dragging and dropping a few items here. So here I've made a sphere. I'm going to say, actually, I want that sphere to have a radius of, let's say, 10. And we can see that automatically updates on my screen there with this level of interactivity. Now, obviously, workflows get much more complex, as we saw, than just generating spheres. But the idea here is that we can start to string together different components to actually create a cohesive workflow here. And now these workflows typically involve things, as I said, much more advanced in spheres. It might be we're going to use a MATLAB script in our process. Maybe we want to use Python. Or, as I said, most often connection to parametric CAD tools. We see people building integrations to, let's say, Creo, where we want to actually take a Creo file and start to parametrically modify that and use that inside our workflow, inside our process. All of these are possible inside Synera today because our goal is really providing connections to every engineering tool that you may be wanting to use in your workflow and your process. So let's dive into the workflow that we've come up with today to come up with this amazing cooling plate design with Diabatix. So obviously we don't start with the end result here. We're going to go back through and take a look at our workflow. And this all started with a simple configurator we started to build out. Now, here, if I turn on the display, we can actually see we've got what looks like a battery module here with a variety of cells packed inside of it. Now, as the user here, we can see I've got my own little function here to really play around with some different properties and parameters here. And we'll dive into actually what it goes into to make this. So I'm actually going to change the type of cells that I'm using, and we're going to see the whole process start to update. Recalculating our KPIs like number of cells, capacity, power, weights, and also most important, our cooling plate that we're actually going to optimize with Diabatix. So here we can see we can play with a number of these different values. Maybe I want to go back and change this to a much smaller design because my ideas for a module have changed. Now, the key thing here is because we've created a function and really encapsulated our knowledge here about this coming out with the first order representation of the battery pack here, we're able to really rapidly iterate. And so, of course, with rapid iterations, you come up with some high-level designs, but then we really have to go and optimize. But let's take a look at what this function actually looks like underneath the hood. So we've actually gone in our user-defined function here and specified a variety of different battery cells that we want to use in our design process here. Now, we're able to define with those battery cells, the name of them, the current, diameter, weight, price per unit, all of these types of things that are going to go into our calculation to help us determine which type of battery we want to use. Now, the other thing is we've gone in and defined some basic geometric constraints that we want to have with our design here. Some length of our pack, the width of the pack, height, some basic configurations that you'd expect for a rectangular module. The other nice thing, though, is if we wanted to, we could select different shapes and use that in our configurator as well, because we've created this own custom function here. Or we could even type in parametric CAD geometry to this as well. Let's go back to the box. Now, throughout the process, we're going to capture some of these key values. And as we start to, in this case, define our own sorting and nesting algorithm, we can see all of the different components of that laid out here in the workflow, very easy to understand. Until at the very end, we start to get into some of the other variables that we want to play with here. So we have the spacing between our cells. I want to use this 2D nesting algorithm because we're going to stack batteries on top of each other, not really a Tetris type operation in 3 dimensions, but rather 2 dimensions. And then at the end of this process, we end up with a variety of outputs that we're calculating here, whether it's the number of cells, the total price, the voltage, and all of this is going to go back into our core workflow. And obviously this is, if we look at it from afar, a pretty, medium-sized complexity workflow. But if I want to consume this now, it's super easy in the end because I've just included this, all of that's hidden away behind the scenes and have a few easy values to play with here. Even, if I want to change the thickness of my cooling plate, all of that's encapsulated inside my workflow. Oh, maybe I've gone a bit too high there. I can't nest all of my cells with the cooling plate I've selected. But we're going to see this again update and start to generate a variety of KPIs here. So the next step of the process is really, okay, we have this, I would say, kind of first level design. Now we need to take that and really start to optimize this, right? And the nice thing is, normally you'd go ahead and maybe define through traditional means a cold plate like this, right? A lot of manual CAD interaction goes into creating this, and we can automate some of that with Synera, but we really want to step this up and get it to a fully optimized design. And so we're going to do that with our integration with Coldstream, where we've set up the entire process for running the workflow right here inside Synera. So it starts with applying our login credentials, pretty standard stuff, but then we get into the nitty-gritty of simulation where we start to apply different materials, material properties, and things like that to the different regions of the model. Again, all of this is set up so it's associative. So as we were to change our configuration coming out of the battery configurator, we'd be able to start kicking off more simulations, more optimizations to really come up with a variety of different designs to help us hone in on what's going to be the exact right fit here. So again, we can zoom out a little bit and just see the process that we've developed quite easily here inside Synera. So defining for the different regions, the different material properties. Of course, what simulation is complete without some boundary conditions where we're going to apply some inlets and outlet flow. And again, all of this really easy to do inside the visual environment here. All of your workflows stored for you. So as you go back and maybe make a few tweaks and changes, it's right there for you to work with. Now, obviously, the optimization process takes a bit more than the 5 minutes that we've been here, but we can take a look at some of the results that we've extracted from the previous designs. And so we can see here a greater delta T between our inlets and outlets through this designed workflow that's been optimized with Coldstream versus the traditionally manufactured one or traditionally designed one that you would do in your CAD tool. And again, the nice thing here is because we've encapsulated this into a workflow, as we start to make changes to those configurations, we can really go back and easily iterate on these design possibilities. And to dive into really the capabilities of Coldstream, I'm going to pass it over to Roxanne to show some of what goes into this optimization process on our side.
Yeah, thank you, Yusuf and Andrew. So I will give you a quick introduction of Coldstream. Well, Coldstream is a generative design tool that you can use to design all thermal and flow problems within only a few mouse clicks. So normally you should now see a slide of how the traditional design loop would look like and how it's comparing with the design loop of Coldstream. Well, a normal design process consists of first, you start with defining a geometry for your design. Then you start simulating it. You need to adjust the design again in order to meet your requirements, but you don't know exactly how you should adjust it. So you do a few trial and errors. You need to recalculate your whole case. You need to redo a complete CFD simulation, and so on. But as you can see, this is a very tedious process, a very repetitive, iterative process, which involves a lot of manual effort. And in the end, you're actually not sure if you have reached an optimal design. You just end with a design that might be satisfying enough for you, but you don't know if there exists any better design. And you also have lost a lot of time with your manual efforts in order to reach to a certain design. Well, with Coldstream, all this is now solved within a few mouse clicks. You basically start with uploading your geometry without any cooling channels defined yet. Then you just specify your boundary conditions. You also specify your design targets. And then that's basically it. Then you just click on submit. Your case will be submitted to a supercomputer where also an iterative design process will start. But it will go towards an optimal design. And when your iterative loop is finished, you will be able to look at your results within Coldstream. But I will now share you my screen so that I can immediately show you a live demonstration of how it would work.
The first thing you start with within Coldstream is your case setup. So in your case setup, you basically set up your geometry, you specify your boundary conditions, you set up your design targets and your manufacturing technique, and that's basically it. So in this case, we will model a battery cold plate. So here we have a base plate, a stamped plate. In this case, it's undeformed yet, but Coldstream will deform it so that it gets an optimal cold plate design. We have a coolant with an inlet and an outlet. And we also have a design region. In this design region, we specify our manufacturing type. We can also set our manufacturing parameters. And of course, in all the other geometrical entities, we specify our material. At the battery modules, we specify heat load. And that's basically it. And then the last thing you need to do is you need to specify your design targets. In this case, we are going to minimize the temperature on our 4 battery modules. And we also want to minimize the temperature variance of the battery modules. And additionally, we also add a pressure loss constraint at the inlet. So a pressure loss constraint of 30,000 Pascal. Once your case setup is ready, you click on submit and your case will be submitted to the supercomputer where it will start running. Once there are results available on the platform, you will be able to look at them in tables. So here you have an overview of the tables that you can look at, but you can also take a look at your 3D results. So here we visualize the optimized plate that comes out of Coldstream. You can do a little bit of post-processing here as well. You can visualize your coolant, pressure loss over your coolant. You can visualize the base plate. You will see the temperature distribution on your base plate and so on. So now what you can also do here is you can download your results and you can download your design as a step file. Now, let's compare this design with a conventional design, which was manually created. So this is quite typical conventional design with straight channels. Let's visualize again the heat distribution on the base plate. When we take a look at the comparison table, so here we compare both results. We have the optimized case and we have the conventional design. When we compare the maximum temperature of the battery modules on of the optimized design with the control of the conventional design, we see that we gain an efficiency of more or less 10% regarding to an inlet temperature of 40%, while keeping the pressure loss below the 30,000 Pascal, which was the pressure loss constraint.
I'm going to show two more slides, ladies and gentlemen, and then we're going to cover a couple of more questions, then we'll call it a day. So what we see by people using Synera, on average, they save 76% in average reduction of development time. And yes, you can achieve the same. You can either go to our website, book a free demo version, 14 days free demo version, or what you can do is to sign up for a free on-site workshop that we've planned for you. So the first 3 people who sign this QR or sign up for this QR code, they can kind of book an on-site workshop. So if you want to have an on-site workshop at your office, maybe wherever you're located, feel free to scan this QR code, and then our team would be more than happy to get in touch with you, talk about your problems, maybe in your product development process, and get in touch with you and tell you how you can use Synera, hopefully with Diabatix in combination, and solve your problems. And while people are scanning the QR code, we're going to hop back. So it's going to be going back and forth the whole time. We're going to cover a couple of more questions. So what is the license structure of Synera? Maybe this is for Andrew.
Yeah, great question. So Synera, we have a token-based system. So really what it enables you to do is have full flexibility in terms of accessing all of the add-ins that we have. So what we don't want to have is that you only have to buy the connector for one product and then you want to use another one. You're not able to do that. With the token system, it's fully flexible. It's multi-user, so you're not singled out to a single person that has access. Your entire team will be able to have access with a multi-user license.
It covers it. Is there any link with Fluent or CFX?
So today inside Synera, no. I don't know if Roxanne, is there a connection with Coldstream to?
Yeah. From within Coldstream, there's a connection with ANSYS Fluent, so you can easily export your case to ANSYS Fluent in order to do some detailed simulations or have some advanced simulation options enabled within ANSYS Fluent.
Great. We can share some material, Roxanne, I think, for the audience after the webinar. Great. Does Coldstream handle two-phase flows? This one is for you, Roxanne.
Yes, well, it's not yet available in the front end at this moment, but it will be released in 1 month and a half. So from within 1 month and a half, you will be able to submit two-phase cases yourself from within Coldstream.
Excellent.
I saw a good one there, I think, at the start.
Go for it.
I think it was, can I see a list of inputs and some calculation outputs? Could we optimize the design using this tool with specific parameterization, like dimensions, size, cooling efficiency, thermodesign, fluid mechanics, etc., to meet all design requirements? Absolutely. I think the beauty of Synera, as I said at the start, is our ability to connect to a variety of different tools. And for some of these things that I see there, like cooling efficiency or fluid mechanics, those are not inherent capabilities inside Synera, but we connect to other tools to enable you to calculate those types of performance parameters. And so what I showed you, obviously, my full-time job is not to design battery packs. It's a simplified example there, but I think you can kind of extrapolate that and say, okay, we looked at some basic KPIs like dimension size, maybe a rough estimate on cost. If we want to take that to the next level then and really level that up, yeah, you're going to start to incorporate those types of parameters. You're going to look at the ability of the module to withstand crash impacts. And maybe we want to then, in a future webinar, we could take a look at, can we create some structural ribs on the side of the module? And of course, all of that updating dynamically as we start to change some of our basic input parameters. So really would be interesting to hear what folks think are some of the next parameters we should add to this little configurator that we've created here.
Yeah, just put all your thoughts in the Q&A box and then Andrew can answer them. Maybe we'll take a couple of other questions, Andrew. Besides Diabatix, what other simulation tools can Synera connect to? I think that's an interesting one.
Yeah, so not only do we connect to Diabatix, we can connect to tools like Nastran, Abacus, OptiStruct. We connect to, some of your typical pre-processing tools for simulation like ANSA, like Hypermesh, that you're going to use in your typical workflow for doing something on the FEA side of things. And of course, not only on the simulation side, but on the CAD side of things, we have connections to every major CAD package, whether you want to read in geometries from those tools, whether it's parts or assemblies, or you actually want to do kind of parametric control of a lot of those tools. We have the capability to do that as well. So you don't lose your geometry in the end, that you have it still as a native file format with those changes going through.
Excellent. Another one would be, I have an electrical system model built up inside Simulink. Can I use it inside of Synera? Yeah,
that's a great question. So today we offer a connection to MATLAB, which also works with the Simulink module. We're talking at this stage also about maybe being able to import FMUs that you may export from Simulink inside Synera to really enable you to have full flexibility of where you want to bring in data and create this connected process and connected workflow from.
I think that covers it. Then we have one, maybe you want to take this one, Andrew. Does the generated design meet the requirement for 3D printing, or do we need to work on the model to make it compatible for 3D printing?
So I think with the models that Roxanne was showing, you have the option to select your own manufacturing requirements there. So you could say you want a design that's compatible with milling or additive manufacturing. There's a lot of options there to really fully customize the output that you're going to get from this optimization process.
I think that covers it. I give it a couple more seconds if you have any remaining questions. And in the meantime, check out synera.io for more information about Synera, and diabatix.com for more information about Diabatix. And we'll follow up with a PDF, the on-demand version of the webinar, and some other material that you can check out. Any other comments maybe from Andrew or Roxanne? Any closing remarks from your side?
Sorry, Andrew, go ahead.
I did just see another question come in before I was going to give my remark there. But yeah, I think what we showed today in terms of a workflow is really representative of what you can do inside Synera. It's all about capturing knowledge, being able to replay that easily, and connecting to all of your existing engineering tools to do that. We're not out here trying to replace those products. We want to make you be able to work with them better than you've ever done before.
I think now that I'm scrolling, there are no more questions. So I think we can now wrap it up. Make sure to check out Synera.io and diabatix.com for more information. And we'll host another webinar on parametric design of eDrives with Synera in around 4 weeks. So make sure to check that out. So thank you so much, Andrew and Roxanne, for joining me today, and hopefully see you soon in another webinar.
Thanks, Joseph. Thanks, Roxanne.
Yeah. Thanks
Thanks,
for
guys.
having me.